Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1666 tract on Fluxions, composed by Isaac Newton during his celebrated Year of Wonders, represents a profound articulation of a new science of continuous change. This document, existing as a private meditation and a tool for discovery, contains the foundational architecture of the differential and integral calculus, framed within a unique kinematic philosophy. Its circulation remained limited for decades, yet its contents reveal a fully operational, if philosophically ungrounded, system for resolving problems that had vexed the greatest minds of European mathematics. An evaluation of this work requires a direct engagement with the specific claims and procedures Newton laid out, examining the internal logic of his creation as a self-contained intellectual system. This essay will proceed with a focused analysis of the tract's principal components, evaluating the claims presented within each distinct phase of his argument, from the establishment of its conceptual basis to its application in solving the most challenging questions of 17th century natural philosophy. Section 1. The kinematic foundation of Fluxions and Fluents. The entire edifice of the 1666 work rests upon a central, imaginative claim that mathematical quantities are best understood as being generated by continuous motion. Newton introduces the concept of a fluent, which is any quantity that changes over time, such as a length, an area, or a volume. The core argument here is that these fluents are analogous to the path traced by a moving point. The velocity of this generation, the rate of flow at any given instant, he names the fluxion. This foundational move transforms the static, Euclidean world of geometric figures into a dynamic universe of processes. The claim is essentially ontological. It proposes a new way of being for mathematical objects. Evaluating this premise reveals its immense power as a heuristic. By mapping abstract variables onto the intuitive, physical reality of motion, speed, and time, Newton provides an immediate, accessible conceptual entry point into the challenging idea of an instantaneous rate of change. The fluxion of a fluent, represented by a dotted letter such as x dot for the fluent x, is thus the speed of excess growth. The framework's strength is its physical immediacy. The argument posits that for any flowing quantity, a corresponding rate of flow exists. This assertion, while lacking the formal proof in the modern sense, possesses a compelling intuitive force that undergirds every subsequent calculation. The conceptual framework is successful because it allows the translation of complex geometric and algebraic problems into a single, unified language of motion. Section 2. The first fundamental problem and the doctrine of moments. Having established his kinematic vocabulary, Newton presents the first of his two great problems given an equation describing the relationship between several fluent quantities. Determine the relationship between their corresponding fluxions. This is the challenge of differentiation. His method for solving it relies on another key invention, the moment of a fluent. He posits an infinitesimally small interval of time, which he represents with the letter O. The amount of fluent, for example x, increases during this tiny time interval is its moment, calculated as the product of its fluxion and the time interval, or O times x dot. To evaluate the claim that this procedure yields the relation of the fluxions, we must examine its application. Consider a simple equation relating two fluents, such as x squared equals y. Newton's procedure involves substituting x with x plus its moment x plus O times x dot and y with y plus its moment y plus O times I dot. The equation becomes the quantity x plus O times x dot, all squared, equals y plus O times I dot. Expanding the squared term yields x squared plus 2 times O times x dot plus O squared times x dot squared equals y plus O times I dot. By the original relation, x squared can be subtracted from the left and y from the right, leaving 2 times O times x dot plus O squared times x dot squared equals O times I dot. At this juncture, Newton makes his most consequential and controversial move. He divides the entire equation by the infinitesimal time interval O, producing 2 times x dot plus O times x dot squared equals I dot. Finally, he argues that because the term containing O is infinitely small, it can be vanished, leaving the final relation 2 times x dot equals I dot. The central claim is that this final equation represents the true, exact relationship between the rates of change. The evaluation of this claim is complex. The procedure is undeniably effective. It produces the correct result. The logical justification offered within the text, however, possesses a functional ambiguity. The quantity O is treated, at first, as a small but finite number, allowing division. Then, it is treated as absolute zero, allowing for its removal from the equation. This dual nature of the infinitesimal moment became the focus of later critiques, which pointed out the logical inconsistency of an entity being simultaneously something and nothing. Within the 1666 work itself, the method is presented as a self-evidently valid algorithm. Its justification is pragmatic, it works, and it unlocks solutions. The internal claim is one of procedural efficacy, a claim that is spectacularly vindicated by the results. Evil as its logical underpinnings remain an implicit promissory note for a more rigorous age. Section 3. The second fundamental problem and the concept of quadrature. The second fundamental problem articulated by Newton is the inverse of the first. Given an equation involving fluxions, find the relationship between the fluents. This is the problem of integration, which Newton conceptualized primarily as quadrature, the finding of areas under curves. His core claim here is that this process is simply the reverse of finding fluxions. If finding fluxions is moving from a fluent to its rate of change, this second problem involves moving from a no rate of change back to the original flowing quantity. This conceptual unification of differentiation and integration as inverse operations is arguably the most profound structural insight of the entire work, forming a fundamental theorem of calculus. To execute this, Newton deploys another of his great discoveries, the generalized binomial theorem. He presented a method for expanding expressions of the form a plus b raised to any rational power, positive or negative, into an infinite series. This tool was of immense strategic importance. It allowed him to take complex algebraic expressions for fluxions, often involving roots or divisions, and convert them into an infinite sum of simple power terms. The evaluation of his claim then focuses on his procedure for finding the fluent of each term. For instance, if the fluxion I dot is given by the equation I dot equals x to the power of n, Newton's rule, derived from reversing his first procedure, states that the fluent y is x to the power of n plus 1, all divided by the quantity n plus 1. By applying this rule term by term to an infinite series representing a fluxion, he could produce another infinite series representing the desired fluent, or area. The power of this claim was enormous. It rendered previously unsolvable quadrature problems, especially for transcendental curves, stochastically solvable through an algebraic algorithm. The evidence he provides within the tract consists of numerous worked examples, demonstrating the method's application to circles, hyperbolas, and other curves whose areas have resisted calculation. The internal logic, as one of algorithmic extension, the binomial theorem creates an infinite polynomial, and the rule for finding the fluent of a single term can be applied to every term in the series. The work presents is as a reliable and universally applicable method a claim that dramatically expanded the domain of mathematical certainty. Section 4. Application to the geometry of curves, tangents and curvature. To demonstrate the utility of his new science, Newton immediately applies it to the outstanding problems of classical geometry. The first such application is the determination of tangents to any given curve. The prevailing methods, from Fermat and Descartes, were often algebraically cumbersome and specific to certain types of equations. Newton's claim is that the fluxional method provides a single, universal algorithm. He defines the subtangent, the horizontal distance from the point of tangency to where the tangent line intersects the horizontal axis. He then argues that the ratio of the fluxion of the vertical coordinate to the fluxion of the horizontal coordinate is equal to the ratio of the vertical coordinate to the subtangent. In his notation, the ratio of id up to x dot equals the ratio of y to the subtangent. By calculating the ratio of the fluxions using the method of his first fundamental problem, he could directly solve for the length of the subtangent and thus construct the tangent line. An evaluation of this claim reveals its elegant efficiency. It recasts a purely geometric problem into a simple algebraic manipulation of rates. The method is direct, powerful, and bypasses the complex constructions of his predecessors. The tract then advances a more ambitious claim regarding the second fluxions, or the rates of change of the fluxions themselves. He uses these second-order rates to develop a theory of curvature. His argument is that the curvature of a path at any point is related to the acceleration of the point tracing it. He devises a formula for the radius of the osculating circle, the circle that best kisses the curve at a point, expressed entirely in terms of the first and second fluxions of the coordinates. This was a monumental step, providing a quantitative measure for a property that had previously been only qualitative. The claim's internal justification comes from a sophisticated geometric argument involving infinitesimals, showing how the deviation of a curve from its tangent is related to the second fluxion. This section of the work serves a crucial rhetorical purpose. It validates the abstract machinery of fluxions and fluents by showing its decisive power in solving concrete, famous, and difficult problems in geometry, thereby proving its superiority over existing techniques. Section 5. Application to extrema. The determination of maxima and minima, another classical problem that Newton addresses to showcase his method's power, is the determination of maximum and minimum values of a changing quantity. A central claim he makes is elegantly simple. At the point where a fluent quantity reaches its maximum or minimum value, its fluxion must be equal to zero. The underlying argument is rooted in the kinematic foundation of his system. If a quantity is increasing, its fluxion is positive. If it is decreasing, its fluxion is negative. For it to transition from increasing to decreasing a maximum or from decreasing to increasing a minimum, it must pass through a moment of stasis where its rate of change is precisely zero. This insight, which seems almost self-evident once stated, was revolutionary. It provided a direct and almost trivial algorithmic procedure for finding the extrema of any function described by an equation. One simply had to calculate the equation for the fluxions and then solve for the values of the variables that made the relevant fluxion vanish. To assess the claim, one sees its immediate and powerful application. Problems of optimization that previously required intricate geometric or algebraic arguments could be solved with a few lines of his new calculus. For example, finding the dimensions of a rectangle with the largest area for a given perimeter becomes a simple exercise. He further refines the claim by considering the second fluxion. A negative second fluxion at the point where the first fluxion is zero indicates a maximum, while a positive second fluxion indicates a minimum. This provided a test to distinguish between the two cases. Adding another layer of analytical power, the evaluation of this section shows Newton establishing a profound link between a physical kinematic intuition, a moment, a rising ball stops before falling, and a purely algebraic procedure. The claim's strength lies in this perfect correspondence, transforming a difficult conceptual problem into a routine calculation and demonstrating the deep structural connections his system revealed between different classes of mathematical problems. Section 6. The algorithmic nature and the unspoken assumptions. Evaluating the 1666 work as a whole reveals a document with a distinct character. It is less formal treatise in Euclidean mould, and more a user's manual for a powerful new set of algorithms. The primary claim is implicit in its structure here as a set of rules and procedures that solve problems. The justification for these rules is overwhelmingly pragmatic and intuitive, rather than axiomatic. Newton's confidence in his methods appears to stem from their internal consistency and their spectacular success in producing results that were known to be correct through other, more laborious means, as well as in solving problems that were previously intractable. The tract operates on a set of powerful, unspoken assumptions. It assumes that all geometric curves and physical quantities are sufficiently smooth and well-behaved to have well-defined fluxions. It assumes that the logic of finite algebra can be extended to handle infinite series without introducing unforeseen pathologies. Most critically, it assumes the legitimacy of the infinitesimal moment O, a quantity that can be manipulated algebraically and then summarily dismissed. This is the behaviour of a discoverer mapping out a new continent, planting flags with immense confidence, and leaving the detailed surveying and geological analysis for later. The work's internal claims are about what can be done, what can be calculated. It presents a unified method for tangents, areas, curvatures, and extrema, a claim of unprecedented scope and power. The very privacy of the document perhaps accounts for its lack of formalism. It was a tool for his own thought, a codification of discovery. A touch of intellectual irony lies in the fact that a system built on the idea of continuous, smooth flow is itself justified by the discrete, logically discontinuous step of discarding infinitesimals. The work is a monument to the power of inspired heuristics. Conclusion. The 1E66 tract on Fluxions stands as a foundational document of modern science, articulating a system of immense computational power and conceptual elegance. An internal evaluation of its claims reveals a structure built upon the powerful metaphor of kinematic generation, which successfully unifies the language of algebra, geometry, and physical motion. Its central procedures for finding fluxions and fluents, though resting on the logically ambiguous infinitesimal O, prove to be extraordinarily effective, providing algorithmic solutions to the canonical problems of tangents, quadratures, and extrema. The work's primary claim is its own utility and universality, a claim Newton substantiates through a masterful demonstration of its problem-solving capacity. The tract's arguments are procedural and pragmatic, prioritizing the generation of correct results over the establishment of a rigorous axiomatic foundation. In this, it is a perfect reflection of its creator's mind, a toolkit of profound insights whose ultimate justification was its uncanny ability to decode the mathematical structure of the world, while the formalization of its core concepts would require the work of subsequent generations. The 1666 manuscript contains the complete, operational engine of the calculus, a testament to a period of unparalleled creative synthesis in the history of human thought. It laid out the fundamental problems and provided the essential methods for their solution, establishing the very framework within which mathematical physics would operate for centuries to come.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.